Welcome to another lecture in the iMath Tutor Screencast lecture series. I'm Dr. Regis J. Sorinko, founder of iMath Tutor. The title of today's lecture is Nothing to Fear Here, Too Scary but Tractable Integrals. Actually, the integrals we're going to look at, I've encountered on Facebook over the past years. In fact, I encountered both of them on the Facebook group Math. Here's the first of the two integrals. Notice it depends on a parameter p. It's the integral from 0 to pi over 2, 1 over 1 plus tangent to the pth power x dx, where p can be any real number. This problem is posted on the Math Facebook group. It's in fact a variant on a problem from the Putnam Prize from a few years back. The other integral, double integral, 0 to infinity, x squared plus y squared, 1 plus the quantity x squared minus y squared squared, e to the minus 2xy dx dy. This was also posted on the Facebook group Math. Someone was looking for a little bit of help in how to do this integral. When you're faced with an integral, one typically looks to see what type it is and then applies the appropriate integration method. For example, if the integrand is the product of two functions, one of which you know how to integrate and the other which you know how to differentiate, you would try integration by parts. If the integrand is the product of a composite function and the derivative of the inside function, so it's the product of a composite function and derivative of the inside function, then you want to try a U substitution. Integrand is a proper rational function, use partial fractions. For two-dimensional integrals, does one order of integration simplify the problem? So is it easier to integrate, say, the x variable than the y, or vice versa? And oftentimes a change of coordinates will make the problem easier to do. Now, if you look at these two integrals, over here, nothing jumps out at you from the standard toolkit. And over here, notice that because of the symmetry in x and y, it doesn't matter what order we do the integration. The first one-dimensional integral you do is going to be just the same, exactly the same integral whether you integrate with respect to x, y. And that integrand looks rather messy. So when an integral doesn't fall into some familiar group, what do we do? The prospects of evaluating it can be pretty frightening, so what do we do? You can manipulate the integrand to put it in a familiar form. Now, for example, if you're taking calculus course, you've probably seen the integral of the secant. Now, just stare at the secant for a while. None of the tricks that you've learned seem appropriate, but if you multiply and divide by the secant plus the tangent, then you see that a U substitution is appropriate, and you end up being able to integrate the secant into the natural log of the absolute value of secant x plus tangent x once you've done the U substitution and gone back to the original coordinates. So manipulating the integrand to try to get you into a familiar form is one of the things that you can do. The other is simply use trial and error. And you want to look at clues as to what to do at each step. Now, for example, if you want to do the integral of the natural log of x, there's only one function there. So you wouldn't naturally think that using integration by parts would work. But here, if you change the integral from u dv, and you let u equal the natural log and dv simply equal dx, you can integrate the natural log of x. So the clue for integration by parts is not present, but yet if you just by trial and error tumble to the integration by parts, you get something that will work with that integrand. The key here is to persevere, though. So if the first thing you try doesn't work, try something else. Keep trying and trying and trying. Up to a point. Then what? Well, you got to give up because maybe it's not elementary amenable to elementary methods, or maybe it's not. It doesn't even have a closed form. If you're looking at the integral from 0 to x of e to the minus t squared dt, that can't be integrated into closed form. So there's not much you can do. But don't give up too soon. If everything you try simply takes you into circles, then you may want to give up. But what I like to do, faced the problem that I don't know how to solve immediately, is commit it to memory, and then in my spare time, think about it. When I run by myself, I oftentimes think about my math problems that I came across during the course of the day that I haven't been able to solve, and many times I'm able to solve them during my runs. So perseverance, but don't bang your head against the wall up to a point. And that the judgment there is comes with experience, when to give up and when to persevere. So turns out that both of these rather scary looking integrals can be evaluated with techniques learned in Penn State freshman sophomore calculus sequence. So this lecture is targeted at people who've gone through the introductory calculus sequence either at Penn State or at their university. So let's take a look then at that first integral. What do you think? Well, it doesn't take any particular form here. I don't see off the top of my head any manipulations. Let's just do a trial and error. Let's try a u substitution. So we'll take u equal tan x. That gives du equals secant squared x dx. And we can use the trigonometric identity secant squared equals 1 plus tangent squared to get the differential. Dx is du over 1 plus u squared. That's after replacing the tan here with u. Now, when we do this, the limits of integration are also going to change. Tangent of 0 is 0, and the tangent of x as x goes to pi over 2 goes to plus infinity. So these limits are going to change to 0. The bottom limit stays 0, but the top limit will be infinity once we do the u substitution. So here we have the transformed integral. Now, are we any better off at this point? Well, if p were restricted to integers, then this is a rational function, and we could use partial fractions to integrate this. But we're not restricting p to be integers. If you wanted to, but you could try to see what's going on here by restricting it to integers, do integration by parts, and see what sort of results you get. That's not what we're going to do. We're going to try another route. So let's use a trig identity to try to change the form of this integral. Let's use the fact that tan x equals 1 over cotan x. So if we make this substitution into the integral, a little bit of manipulation brings us to, changes the integrand to cotan to the px divided by 1 plus cotan to the px. Doesn't seem to have helped us any, but again, let's try a u substitution. And this time we'll do the u substitution cotan x. We're going to skip the details, so we recommend at this point that if you'd like, you can pause the slide and verify that this is what happens. This is what you get after you make this u substitution. Now, looking at that, again, if p were a integer, we'd have a rational function, and partial fractions could be used to integrate it. But we're not restricting p to the integers, so looks like this route doesn't get us anywhere any better. So let's take a look, but before we move on, let's compare the two results that we found. So we have that two different ways of expressing this integral. In one case we have 1 over 1 plus u squared, 1 plus u to the p for the integrand. And over here, the numerator changes to u to the p, same denominator. If you look at that long enough, you might realize that 1 over 1 plus u to the p plus u to the p divided by 1 plus u to the p equals 1. So if we add these two integrals, use the linearity, factor out, take out the common factor of 1 over u squared, lo and behold, we end up with 2 times the integral equals the integral from 0 to infinity, 1 over 1 plus u squared du. Now this integrand, we know integrates to the arctan. Arctan of 0 is 0, and the arctan approaches pi over 2 as its argument goes to positive infinity. So 2 times this integral integrates to pi over 2, and hence this integral is pi over 4. Turns out not to be that bad. So notice here, this is just a case of not throwing away results that we had. So two different approaches led to two apparently intractable integrals, but put together, we were able to come up with a solution. Now, let's play around with this integral some more and see if we can come up with another way of doing this integration. Let's use a different trig substitution. Here we're going to, trig identity. Here we're going to use the fact that tan x equals sine x over cosine x. If you substitute that in for sine x, multiply through by the cosine, the power p, we get this integral. Here, it doesn't look like we've improved our situation any, but we can use additional trig identities, noting that the cosine of x is the sine of the quantity pi over 2 minus x, and the sine of x is cosine of the quantity pi over 2 minus x. We can change the numerator to a sine, and the denominators doesn't really, this will switch to sine, that'll switch to cosine. And then use a u substitution. X prime equals pi over 2 minus x. When we do that, this is what we get. I dropped the primes integration variable. It doesn't matter what I call it. And by dropping the primes, we keep things a little uncluttered. So notice here, this little trick gives me, changes the numerator, but keeps the denominator the same. Now, let's add the two together. And when we do that, we end up adding the numerators. So you end up with sine px plus cosine to the px divided by the same quantity. That's 1. So you end up with the integral from 0 to pi over 2 dx equals pi over 2. Or the integral equals pi over 4, as we found before. This trick, we didn't even have to do a very complicated, when we actually had to come down and do an integral, it's just integrating the constant 1, which is very simple. So the second approach is even better than the first so far as simplicity, but not obvious. So you have to play around with it, play around with ideas to arrive at it. So now let's move on to the second integral. As we said, when you're faced with two-dimensional integrals like this, you can turn them, using Fabini's theorem, you can turn them into iterated one-dimensional integrals. And sometimes by choosing the first variable to integrate over, you can simplify the problem. But notice here, this integrand is symmetric in x and y. So it doesn't matter which way we do it. And we can't there's no way to factor this integrand into a function of x alone and a function of y alone, which would be nice. So just not clear what to do. So let's just take a shot in the dark and change to polar coordinates and see if that makes our life any easier. So when we do polar coordinates, the differential turns to r dr dx. X is r cosine theta, y is r sine theta, so we end up with r squared cosine theta sine theta, replacing the x times y. X squared plus y squared is r, and here x squared would give me r squared cosine squared, y squared is r squared sine squared. And I've got a square out here, so when I pull the r outside, I get an r to the fourth. Now let's look at the limits of integration. We're integrating over the first quadrant. X goes from 0 to infinity, and y goes from 0 to infinity. In polar coordinates, the first quadrant, theta goes from 0 to pi over 2 in the first quadrant to get the first quadrant, and r goes from 0 to infinity. So there are our limits. Now at this point you might think that's not much better than what we have there. But we can use double angle formulas to simplify this. So we have the trig identities that 2 cosine theta sine theta is sine 2 theta, and cosine squared theta minus sine squared theta is cosine 2 theta. So if we do that, now things are starting to look a little more tractable. But we're not quite there. Notice here I've got an r squared sine theta. Now, if that were an r, that would just be y. And if this were an r, that would just be x. And it would look like we'd be starting to be able to separate the integrand into a function of x and y alone. But we're not there yet. So why don't we do a substitution. So what we'll do is we'll let r prime equal r squared and theta prime equal 2 theta. Now, when we pretty much, so this is just going to be sine theta prime, that's going to be r prime squared cosine theta prime. That the differential here, r dr, will become my dr prime once I multiply and divide by 2. D theta prime I have to multiply and divide by 2. This r squared will become an r prime. So now the limits on theta prime are 0 to pi over 2. Limit on r prime doesn't change. So what we've done here is I've taken this r prime and moved it over to my new differential. So I notice here that the differential is for polar coordinates. Here, that's x. Here, I'm sorry, here that's y. Here that's x. This would be a function of x alone in Cartesian coordinates. That would be a function of y alone in Cartesian coordinates. So let's transform back to Cartesian coordinates. Notice, however, now that we're no longer integrating over just the first quadrant, we're integrating over the first 2 quadrants. So we'll have to change the limits appropriately when we change back to Cartesian coordinates. And lo and behold, I have a function of y alone, a function of x alone. So now I can change this into 2 one-dimensional integrals. This one integrates to 1, this one integrates to pi. Together we get pi over 4. So as we see, we have nothing to fear here. These seemingly difficult and frightening integrals were actually not that hard to do. Just a little bit of trial and error and paying attention to what we do so that we can put things together to get the answer. Now a word from our sponsor. Some of our services and products offered by iMathTutor are face-to-face tutoring for any university student for university students and professional that can meet with us in State College, Pennsylvania. Online tutoring for university students and professionals worldwide. Quick reference guides and practice exams with detailed solution sets for Penn State Math 141, Calculus with Analytic Geometry 2. These are distributed by Nittany Notes. You can visit them online at www.nittanynotes.com. And we'll add more study material for other courses as demand dictates. So if there's enough of you who need something and you tell me about it, we can get it out there for you with any luck. You can also contact us to arrange a free consultation by visiting our website. There's a consultation request form there. You can also learn more about iMathTutor at our website, imathtutor.org. If you prefer, you can email or call us. Our email address is help@imathtutor.org, and our phone number is 814-317-6284. Thanks for watching, and stay tuned for more screencasts to come.